Now, the reason for picking 10 is that we can't get them all into the registers. See, if you had 5 of them, you could just load each one of those into the register and then do your ads in the registers and work it down. You'd be okay. Here you can't do that. One of the things that one might think of doing. Let's look at strategy.
So how many registers can we use?
Well, there are 8 registers. In theory, you can use all 8. Here's one strategy. Put a label on each location. Say A1, A2, down to A10. Then load and add each. Remember that the add instruction, as you look at it, the operands for the add have to be either in a register or immediate mode. You can't just add from memory directly to an accumulator in the register. Okay, so if we follow this strategy, we'll start, we'll start in the traditional place. We'll load, we'll put our sum into register 0. So we'll begin our sum just by loading A1 into there. Okay. Then we'll load register 1 with the second value and add the second value to the first value and put it in register 0. Then we'll load register 1 with A3, add register 0, register 0, register 1. You get the idea? A4, add. We can do all 10 of them that way, right? Now, based on experience in working in high-level languages, when you see something like that, what do you think of?
Loop.
Loop! For heaven's sake, let's use a loop on this thing somehow. Okay, so we're going to modify this thing a bit. We're going to say, let's use a loop on this thing somehow. Okay, so we'll go back up to here. That first step is probably best. An alternative would be to clear register 0, and then as part of the loop, load that first value and add it onto register 0. But this is much more efficient. Now, our real problem here comes from addressing those different memory locations. Okay, somehow as we try and fetch each of those values into a register so that we can work with them, Let's see, I've said there were 10, so we have 9 more to go here. So I'm going to I'm going to get a loop counter in here. Oh, let's do this. I'm going to add another thing here as I think through this process and figure out how I'm going to do it. I'm going to say, we've got each of those 10 things down there. I'm also going to include a location, we'll call it N, which has the number of values to work with. That way we can use this same program to do 10 or 100 or even 1,000 values without changing the program. We just change the data. Okay, so I'm going to use register 3. Here's my loop counter. Why did I use register 3? Totally arbitrary choice. Just seemed like a good number. Now, I've already done one of the values. So I actually need to subtract 1 from it. So it now says I have 9 more values to add. Okay. Now I'm going to use an instruction that we haven't talked about. LEA says load effective address. What this is used for is to get into one of the registers the full 16-bit address of some memory location that you want to work with. Okay? Remember, most of the ones that we have worked with have used an offset from the PC. We've mentioned briefly the other addressing mode that works from another register, but here we'll, it's not an offset. It's going to get the full actual address of the thing into that location. Now, as soon as I say that, when you look at the binary representation of this thing, it has an offset in it. Let's see, I said that these things were labeled this way. We've got A1, so I'm going to load A2. Now, if you look at that thing, the binary representation, let's see, the code is 1110. And then you've got your destination register. And then you've got a 9-bit offset. Now what this instruction does, you remember those offsets work from the PC. So it takes the contents of the program counter, extends this 9-bit offset to 16 bits and adds them together. then with a typical load, as in one of these two, it takes that value and puts it in the memory address register and pulls the contents of that memory location out. The difference with this thing is, does the sign extension on the offset, takes the PC, adds them together, and puts the result in register 4, instead of in the memory address register.
Do you want to show an example? Just
This what?
want to show an example on the board?
Yeah, I will.
Okay.
Hang on to it here and we'll get an idea here of what's going on. Okay, so that gets the address of register 2 into register 4. Now, here's where I'm going to begin my loop, and we'll work through this thing. Now, I'm going to use that base register addressing mode. Let's see if I can get you to a reference where they show you how to write that thing. Those are all binary, so it's got to be in chapter 6. Don't even see it there. No, here we go. Well, there are lots of examples of code in here, and none of them use that addressing mode. That's kind of cheap. Let's see if I can find a specific reference to it.
What's the code for?
It's the LEA, that one.
That one's not very helpful. And I think this one. Okay. Look on page 533. We use the instruction LDR, load relative. We're going to load register 1, and the thing looks like this. It says, I will use the contents of register 4 as a base address, and then I will add a 0. what's in register 4 and then fetch from that location. Then I can add register 0, register 1. Now, I'll decrement my counter. Well, no, wait, I want to do that last, because that's where I'm going to base my branch.
So
Okay,
on the,
leave a space here, I'm going to come back and put in an instruction in there.
so on that LDR, we're looking at register 4 and taking what's inside register 4 and then adding 0, and then it's going to go to that location,
Yep.
and that's going to be loading what's those contents in that location to register 1. Is that
It
correct?
doesn't add it to, it sticks
No,
it into
it sticks it
register
into
1.
register.
Yeah, copies it into register 1.
Make sure I got that.
Now, my loop counter, as long as the thing is positive, I want to branch back on to my loop. They write it with a lowercase p. I think it'll work with an uppercase. Branch is positive. To loop.
That's the actual code you write for that?
Mm-hmm.
So the NZP is that little,
Yeah, and if you want to branch negative, you say BRN.
let's see.
If you want to do branch greater than or equal to 0, you would say
P.
branch ZP,
Can you do
0
PZ?
or plus.
Wouldn't matter if you did PZ.
I don't know. Try it and see.
That's good.
That's one of those interesting things that sometimes give people feelings of insecurity. But, you know, if it doesn't like it, it'll just tell you when you go to compile, to assemble the thing, it'll say invalid instruction. And you can write it the other way and then you're okay. Now, the problem here is, as I go back up here, I'm going to fetch the same value in. And I don't want to do that. I want to change that thing so that I go down to the next value. Now, there are two tricks to this. I'll show you the hard one first, and then we'll, because it illustrates a significant factor here. In this gap right in here, I can do the following. I can load register 5 loop. Now, I want you to remember, and this is the point of this little discussion here, I want you to remember that all the computer sees is a pattern of zeros and ones. It doesn't know if it's instruction, data, floating point number, integer, character, doesn't have a clue. It's all in how you do it. So it goes to this memory location and loads that bit pattern into register 5. Cool. Now, let's look at that instruction in register 5 and just see what we've got there. it looks like this. The load relative is opcode 6. And then you have your destination register, your base register, and then this constant. Six-bit offset, yeah. Okay, now if I load that into a register, I just have this bit pattern in there. It's a number, can be seen as a number. I add 1 to it, what's it going to become?
The constant will change to,
I'll just add 1 onto the end of it.
awesome.
Okay, so that load is just loading that whole instruction into register 5.
That's right.
Okay.
I add 1 onto it, I store it back in. Now, all of a sudden, when I do this branch, this offset is no longer 0. It's a 1. And so now, it's going to take register 4, which is kind of the beginning address of things, and it's going to add 1 onto it, so it's going to look at the next memory location. Now, we had a request here to trace this thing through and see what happens, so let's do it. We're going to store our result.
So are we still in the hard part, or have we?
Yeah, there's an easier way to do it.
That seemed pretty good.
You just increase register 4.
I love that.
Okay, let's just see here where we are.
You can do all that.
If this is location 3000, and this is 1, 2, 3, this is 3004, 5, 6, 7, 8, this is 3009, this is A, this is B, this is C. So now we'll start here at D. I don't know in what order we've got these things stored. It really doesn't matter. For the sake of discussion, let's say that N comes first. We've got a 10 in there, and then at 300E, well, okay, we'll call it A1. A2. A3, we won't attempt to write them all down. And so on, and then down there at the end someplace, I've got a location that I called sum. Okay, now let's watch what happens to this thing. I'm assuming that these go right in here. Register 0, 1, 2, 3, 4. No, yeah, we do go to 5, don't we? Register 5. Okay, first of all, we load the value from A1, which is into register 0. That's not binary in spite of the fact that they're all zeros and ones. I'm assuming it's a hexadecimal number. You see the hex there. Okay, so we did that. Now we'll load register 3 from N. So register 3 has A. And then I added a -1, so it becomes 9. Okay, now, let's, in order to go through this effective address thing, remember how it works, and we'll actually figure that offset, and you can track the thing through and see what's going on. The address of the next location is 3004. The one I'm looking for is 300F. Okay, so what do I add to 4 to get F? 11. Okay, so our 9-bit offset is looks like this. Well, let's see. Let's just point out here that as we are executing this instruction, the program counter contains 3004. How does this thing work? It takes this number, copies this bit over and over again until it has 16 bits, and so it has 000B. Adds that to what's in the PC. It does not do the adding in the program counter. The program counter doesn't change, but it adds these things. 11 and 4 is 15. Now, on a regular load, either one of these, it takes this and goes out to that memory location and fetches the contents. In this case, this is what gets put into register 4. Okay? Instead of going out to memory with it, it just sticks it into the register. Okay? Very common thing. If you think in terms of some of the work you've done in C++ and so on, we're kind of working with an array. And this is a common approach. You get that full 16-bit address of the beginning location of your array, and that's what you work with. Okay, so we got that taken care of. Now, this one says, take register 4, okay, we'll go out and use this form, register 4, extend this thing, add it, go to that location. It's the same trick we did here, except that we're using register 4 instead of the program counter. Well, adding 0 just says that we go to 300F, that's down here, and we put that value into register 1. Then we add register 0 and register 1 together and put the result into register 0. So we have 01A5. Now we load register 5 with this thing. Let's see if I can get that into hex. It's 6300. Emphasize again, yeah, it's an instruction, but it's still just a bit pattern. And so it just sees it as this number, particularly as we go through now and do arithmetic on it. we now get 6301. And when I store it back to this location, this number now becomes a 1. You'll never see the actual instruction change, I don't think, the printout of this assembly language thing. But effectively, we've changed that where we're now looking at a different location. Okay, now we add -1 onto register 3. It's still positive, so we go back up to here. Now you see as I load register 1, it's going to be what's in register 4, 300F, plus this thing. So now I'll go to 3010 down here, because I've changed the offset there. So now I load register 1 with a 0019. Because I have changed the instruction. I modified the instruction. Now, next instruction is to add registers 0 and 1 together. 14B10. Now I go through this process again and add 1 in, and now this offset becomes 2. I didn't fill out any more values, but we would go through again and find the next value, which would be at 3011, because I'd be adding 2 onto F. Get the next value in the array, and so on as I count down through it. Okay, clever trick. What it amounts to, this becomes what we sometimes call self-modifying code.
The code that you have now, is that ever going to stop, or is it an infinite loop currently?
Yeah, it'll stop, because this thing will eventually come down to 0. And this is what's controlling my loop, is this value. And it's being decremented by 1 each time through the loop. So it will eventually reach 0, and then it will not execute this branch and go down and store our result. Now, there are some philosophical problems with self-modifying code. One of the problems is that self-modifying code is really hard to debug. If it doesn't work right, you know, going in and looking at what's in a memory location can get really confusing, because what you see after executing this a couple of times through this loop is not the same as what your code listing says it is. And so it's kind of a questionable way to do it. So here's an alternative way. Let's just say and now we'll not put that in there. And so the difference will be, instead of going through this, I'm going to continually actually modify this location, this address that's in register 4. And will always be offsetting 0 from what's in here. If we go back and start through again as we get to this point, we just go back to here and start through, It says load register 1 from R4 plus 0. Well, that's 300F. Okay, so it's 00A4. We add that on to register 1. So I get 01A5. Now I add 1 to register 4. So I'm at 3010. Subtract 1 from my loop counter, which was here, gets us down to 8. It's still plus, so I branch back up, and now I load register 4 plus 0. Well, register 4 is now different. And so I go down to 3010 and I get, I'm loading register 1, 0019, add it. Increment register 4 again, 011. Decrement this thing, 7, still plus, so I'll loop again.
Those values you have down there, 0101 and the 0084 and all those, are those are addresses or are those actual
No,
values
those are the actual values that I'm adding up.
that you plugged in there? Just
Yeah, I just made up some
arbitrary?
numbers,
Okay.
yeah. Just whatever number you come across. Okay, now, let me point out something about working in C and the similarities between working in C and what we're working with here. Like I said, we're more or less working with an array. What I've done here is to get the starting address of the array. If you wish, this is the index. If you say that you want A3, the starting address of the thing goes here, the index goes here. And that's one of the reasons why in C, in a lot of the languages that were developed before C, and C of course is the parent of C++, we started indexing arrays at 1 rather than at 0. But boy, if you start at 0, there's no translation involved. You just take the actual index that you've got, plug it in there, and go. You don't have to add anything to it, you don't subtract anything, to index it in the right sequence or anything like that. It's just plug it in and go. And that's one of the reasons why they do it that way. It's just easier to work with. Because virtually any array application that you're working with in assembly language is going to work something like this. That you're going to have the base address of the array, the beginning address of where the thing starts, and then your index subscript kicks you down into there a certain distance. Now, in byte addressable things, it's not quite a direct thing. You have to multiply by 2 or 4, depending on the size of your things and so on. But still, it's a pretty direct transformation. Pretty direct. Which, of course, is one of the reasons why we have you all taking assembly language in the first place, is to know how these things work in the higher level languages. Okay, any questions about this? Well, you can see, logically, this one's a little easier to work with. This one, however, leaves my base address, the base beginning of the array, unchanged. But it does modify the program. See, if I do this one, if I get through that array and I want to go back and do something else with the array, I'm going to have to reload the starting address of it someplace because I've destroyed it in my processing. So there are, as for example, if you're trying to find mean and standard deviation, do a typical statistical study on this thing, you're gonna want to sum the thing, you're gonna wanna sum the squares, or go through and find the mean, the average, and then sum the difference of each score from that average, and add those up. And you may wanna work through the array a second time. So, there are pluses both ways, but, again, generally, we tend to worry a little bit about self-modifying code.